ultra-fast X-rays. And we are very much looking forward, Jens, to your presentation.
Okay, thank you for the very kind introduction. It's a real honor for me to be here, and I hope I will not bore you with my perspective on, I think, what can be done, what is new, what is interesting with the Attosecond sources that we were developing, and there is a lot of complementarity and connections to what you're doing on user facilities, FELs, and so on. I tried, before I share the slides, I tried to find a little bit of a balance between, so it's not just a conference talk, of course, but also give you my view. And I looked at a few previous presentations from Francesca, from John Marangas, but also from Anders Nielsen on some of the X-ray physics. And I tried to find a little bit of a way around it in order not to hopefully duplicate. So let me share my screen briefly. You see, can you see the slide, the presentation?
It's perfect, Jens.
Okay, so let me maybe show you the menu first. So I'll try to tell a little bit or talk a bit about the questions, challenges, and the methodologies, and why I decided to pick what we're doing, and give you some of my perspectives here. Then I'll tell you a little bit about Attoscience technology, how it came out from certain laser sources and what are the pros and cons. And then I'm very excited to share with you some recent breakthroughs, especially also in my group, that some unpublished results to show you what's possible. And then maybe some prospects for us. I would say us, I call myself like the tabletop sources, harmonic generation based sources, but also for FELs and what can actually, and I think should be developed together. And there are many opportunities here. Let me start with a motivation. So why do we do these things? And especially Attosecond technology and also these big light sources, they're not cheap. We should be trying to, aside from just having fun, also try to address some important questions. And I'll give you maybe 4 examples here. Totally different areas, but you'll see they have a unifying theme. So if you look at energy harvesting, solar cells, organic solar cells, you know, they are interesting for many reasons. One of the big issues there is efficiencies are low. I think it's a bit higher than 15% now, maybe 17, 18%, but it's still not 80, 90% or 50%. And some of the questions deal, I don't want to go into all the details. I don't know, do you see my cursor actually when I move the mouse? Well, if
yes, we do.
Okay, good. So one of the questions is, of course, related to, is the light not efficiently absorbed? Do you generate this electron hole pair and you have some charge trapping at some point? Is it a problem with transport? So there are a gazillion techniques that you can apply to this. At the end of the day, we still don't know exactly what is the core issue or what are the connected core issues. Another example. Chemical functionalization. The products that we're using every day are used through different chemical processes, and about 19%, 20% of the global energy budget goes actually into chemical industry. And so this is one of the oldest streams that is discussed in physics or in chemistry for a long time, is can you manipulate, can you understand reaction pathways? The field of coherent control tried this, was not very successful, I would say, with it, because it's a very complicated multi-body problem with correlated dynamics. Another one that we're also trying to address, like probably a few of you, is electronic transport. If you look at it, if you look at consumer devices, if you look at electronic circuits, there's problem with ballistic transport, scattering. And in fact, the growth of consumer devices and global internet actually demands an increase in energy budget, which is absolutely not possible, not even taking into account that we should save energy and reduce wasting energy. And then there are, I would say, fundamental new possibilities. You might have heard about the twistronics field that emerged from basically 2 layers of graphene. And people have found that when you change the, let's say, the orientation of 2 layers with respect to each other, Basically, you change the dielectric environment, Coulomb interaction, and you can influence band structures in a way that you can get transport much alike in superconductors. And it's nice, I wrote here serendipity, not to be derogatory, right? It's nice to develop this or to find it by accident, but if we want to address problems like this global energy consumption, of course, we have to find an engineered approach to address these problems in a planned way also. And my argument, and obviously I wouldn't be here if I wouldn't believe in it, is that light science can provide some solutions and some new tools for that. So let me step just a little bit back here first as a quick reminder. So whatever we talk about, of course, you will see in the next couple of slides what I'm getting at. Electronic structure that we talk about in solids or in molecular system arises, of course, from the arrangement and the type of atoms. You have nuclei of different species that you arrange in space, and their interaction essentially determines the electronic structure. And I've stolen some from Khan Academy here that shows you the transition if you go from atoms to molecules to solids, and you know this all from your lectures, basically the emergence of bands. My point here is that these things are coupled very strongly, sometimes a bit more weakly through Coulomb forces. And in chemistry, if you can say, well, electrons move fast, nuclei move slow, so we can look at these interactions in a separate way or with different techniques. You call it the Born-Oppenheimer approximation. But my argument is that in most of the interesting cases, and the ones I presented before, you cannot make this approximation. It breaks down. You have to consider correlations. Nuclei don't just move slow, even though their mass is much higher than the ones of electrons, and you have to consider that. Then just another quick reminder without going into too many details. I show you here just basically a layer of titanium disulfide. This is one of these quantum materials, titanium disulfide. And essentially, if you look, it consists of covalently bonded titanium and sulfur atoms. And the atoms that, so to speak, determine the action here is the hybridization between 3D and 2p orbitals between the different species. Point is that the orbital overlap, the sharing of electronic density, determines the properties of the material, whether it's metallic, semi-metallic, insulating, whatever it is. So in order to try to address these problems that I mentioned on the previous slide, you really want to be able to say, okay, I want to see what is happening where the charge really moves. I really want to see whether the material is semi-metallic under certain stress or something, or what happens when I adjust the magnetic field. So what I tried to say in the last two slides is already, and you have seen this, you need to essentially to disentangle these problems and address them from a different angle. You need to be able to look at electrons, holes, or their coupled entities, excitons, their interaction with lattice or nuclei. And sometimes if you're interested, you know, magnetism is not just slow, as many people say, especially if you have heterostructures. It can be very fast. And these things are all coupled. And many times we make arguments that electrons are very fast. We can look at this with Attosecond sources. Then you might use Raman spectroscopy to just look at the lattice. And then you can try to piece this information together. And my argument is that this is exactly the problem, that many times this is not just true. So we need some kind of tools to disentangle these interactions. And the argument that I will make is that actually X-ray spectroscopy is a very powerful tool that can address this. And I'll show you some of these examples later. Another argument that I want to make here is in most of these experiments that we're making, we do some kind of pump probe experiment. We disturb a system out of equilibrium, and then we try to watch its evolution. And that has basically one assumption, is that this is repeatable. And the other one, my argument is that this disturbance, the pump, in our case, for example, it might be a light pulse, it might heat the sample to generate a Mott transition or something else, is always the limiting factor. It's not typically the probe, it's the pump, because you have to apply a certain amount of fluence, a certain amount of field strength to reach an excitation fraction. And then you should ask yourself, well, do I achieve enough excitation to be able to see a change with my method? Do I excite multiple states at the same time? Can I disentangle what I really was doing there? And then there are other technical issues that are related to it in terms of jitter and repeatability and so on. And then one of the questions is, of course, what do I probe with? What out of the different methods? And I just want to break it down between basically charged particles, electrons, and photons. Of course, with electrons, they have extremely high sensitivity because the interaction cross-sections are about 5-6 orders of magnitude larger than with photons, give or take. However, the problem is that typical electron sources, you need more than one electron to image some or to measure some absorption or some scattering. And then if you have a bunch of electrons, they repel each other, that limits temporal resolution. And if we look at these very fast dynamics, let's say femtosecond, tens of femtoseconds, that's an issue. However, it gives you fantastic spatial resolution because of the de Broglie wavelengths of the electrons. I mean, even with kV or so, you can get easily picometers. Detection needs care because you're dealing with charged particles. Photons have much lower cross-section. However, the spatial resolution is not as good at all. If you're after short time resolution, you can generate attosecond pulses with it. And detection, I would say, depending on what you're doing, of course, can be relatively simple and is established. So X-ray spectroscopy is something that seems to me very nice and powerful. And of course, it's done at synchrotrons for many decades. And the people there have developed this field to a fantastic detail. What we can now bring in is maybe a different thinking, a different additional opportunity in terms of not only the time resolution, in terms of also the bandwidth that we can use and leverage. And so just in a nutshell, very briefly, because Anders Nielsen has done a fantastic tutorial and talked about all the different aspects of it. Let's assume that I have a certain material and I show you the electronic structure there in a very simplified way. And let's assume the action is, let's say, because of an electron being put in this 3p state or not. And I want to know only that. And I don't want to know anything else that happens there. So remember my example with the titanium disulfide. So I can do some photoemission studies. I can send some X-ray photons in and measure charged particles, the electrons. This is a nice method. It's element selective. So I know I'm looking at my titanium species, for example, and not at the sulfur, or I can pick it. It is state specific, certainly. It is surface sensitive. That has pros and cons. If I use X-rays, I don't have a final state core hole. I'm limited maybe in the pulse duration and in the resolution. It needs UHV. So this might be a perfect method for some of you. Then there is a method that undoubtedly at FELs is a hot contender for many reasons, which is resonant inelastic X-ray scattering. The nice thing here is essentially you measure just photons, photon in, photon out. Again, it has all the advantages written in black. The great advantage here from a measurement and interpretation perspective, and I'll get back to this later, is it leaves no final state core hole. This means the electronic structure is not changed very much. So what you measure is really a very nice representation of the electronic states that characterizes your system. However, again, there are limitations in terms of temporal resolution, and some might be mitigated by techniques that are being developed very actively, for example, at the FELs. However, this is a photon-hungry technique. So for us, for harmonic generation, this is not something feasible at the present time because we're limited in photon flux. So the method of choice for me and for us, for many of us, is X-ray absorption fine structure spectroscopy, which is again photon in, photon out technique. And it has all the nice advantages, again, written in black, that I don't want to repeat. However, it leaves a final state core hole. And I would argue that in most cases, because this can decay very fast, it's not a big deal, or it's even interesting to use that and to study it. And of course, there are techniques like core hole clocks and so on. However, it allows us to use the full power of having attosecond pulses, not just, again, I emphasize this probably 10 more times, not just the short pulse duration, but especially the broad, coherent spectrum that comes with it. And I took this from the book of Joe Stir and Harmonic Generation about the method being element and state selective. This is a simple example that they did, where if you look, for example, at benzene ring, you have these in-plane sp hybridized orbitals, or these pz orbitals that essentially stick out of the plane. And if you have linearly polarized X-ray pulses, and the X-ray field is aligned along where you have electronic density, meaning along this, this wave function, along this orbital, you can interrogate one or the other state. I find this actually quite amazing, even though it's simple, right? That you simply essentially turn a material or a solid and you just look at specific orbitals. And you can do this here in the absorption spectrum, that they see this pi star states or these sigma star states. And when we started developing our sources, we just tried this in some graphite, 60 nanometer freestanding graphite. And you see here, for example, for 3 different angles of the X-ray field relative to the surface at 0 degree here in pink or violet, and then 20 and 35 degrees, you can clearly see how this pi star state can get selected, or how we can actually look at both of these states. Here already you see I wrote 1 minute integration. This was one of our first experiments. Now this goes in a couple seconds. It's not a tremendously broad spectrum, but we don't have to scan anything. You just measure this at once, the whole spectrum, which is one of the advantages of using an attosecond pulse. Very quickly, as I said, X-ray absorption spectroscopy, how I want it to be understood, and that's not necessary. It's maybe clear for you in the FEL community, but maybe not so clear sometimes in the attosecond community. And I'll get now, I'll rant on a little bit about this, is that it should be really understood as a core level spectroscopy to interpret it in the way that I want to interpret it, to be element specific. And I give you the example, essentially how it works. Assume here you have a synthetic carbon atom. Carbon has 6 electrons. The 2p state is not fully filled. Now, if you have X-ray photons with sufficient photon energy, and assume it's monochromatic, but you could turn this photon energy, at some point you might hit a resonance and you can promote a 1s electron to a 2p state. That's dipole allowed, electric dipole allowed. And you would register this essentially in an absorption spectrum as a peak, right? Or photon is missing directly. And by reading out these peaks as function of photon energy, you can essentially interrogate the electronic structure. So where electrons can be promoted to. And if you at some point increase the photon energy such that you hit the ionization threshold, you have a huge change in absorbance. And if you are not in a single atom, but you have a liquid or a gas, a molecule, or you have any solid, the neighboring atoms can actually modulate the absorption cross-section, and you register this as an oscillation. And again, this has been given different names: X-ray absorption near edge structure, or extended X-ray absorption fine structure. XANES is also called NEXAFs, depends a little bit on history and the community. My point is simply that the X-ray community has developed a fantastic understanding how to pull out of this information about the electronic structure, as I told you, the excitation, if for example, some more electrons or more states are occupied, this is also registered as a change in this kind of peak here. If you have a structural or an electronic phase transition, this should register there. You can get electronic structure, bonding, you can get the nuclear and lattice position, vibrational, vibration, structural phase transition, all of that out. And we have used this broadband pulse that we get automatically when we generate attosecond pulses to measure all of these simultaneously and showed this at least as a concept. Now, I want to make a few points why we really need high photon energies, why we shouldn't be doing this with 10 or 20 eV photons, in my opinion. And there are several reasons. I just show you a very simplified picture here where you can have these different edges. So essentially the 1s electron in whatever material is the most inner bound electron, and transition from there are called K edges. And then if you use, for example, 2p states, there are L edges, M edges, and higher lying edges. And if I now want to probe, for example, what's happening between a conduction and a valence band in a solid, right, or around the ionization threshold, maybe some Rydberg states, and I do not use 1s electron or 2s, 2p electrons or something like this, meaning states that are far away from where I want to measure some changes, then I also deal with parasitic ionization at low photon energy. So I basically pollute my signal through additional ionization, which is unavoidable. Another and bigger problem, which is known in the atomic physics community, are multiplet effects, which change the spectral shape and the branching ratios. And I'll give you one example. I just calculated briefly for you the band structure of IPCO. That's a superconductor, but pick anything else. And I don't want to go into all these states and so on. My point that I'm trying to make is, if I want to learn something about this material, I'm interested somewhere to look up there. You can't totally read it, sorry. It's so here is basically, if you will, conduction band, or where the action happens in this material when you cool it down and you see a phase transition. Now, if I would probe this, for example, IPCO, different species, maybe I want to measure at the oxygen edge, or I want to measure at some other edges. If you look here, this is the K direction, so the inverse space for the solids, or basically space direction, if you will. The core states are dispersionless. They're basically just flat lines. And if you go to the 1s state of one of these elements, they only contain basically a spin up and a spin down electron. And with that, you can probe whatever unoccupied states you have up there. So the core states are essentially dispersionless, and you have a well-defined initial state. You know, I start from one state only, and I probe whatever states I want to probe. If I just zoom in, this is the same calculation. I just looked at basically the area further up there in this, what I call semi-valence states. And let's say you have a source, an FEL, or maybe a harmonic source, more likely at 20 eV or 40 eV. You're basically taking electrons from any of these states that have a clear dispersion, and you're gobbling it up there to probe any unoccupied states. And so this makes the interpretation very difficult and sometimes impossible. And so the problem is, for example, if you look at titanium dioxide, you can probe for example, the 3D levels with 3p electrons. This has been done and published. You already have 45 different transition or final states that determine the spectrum that you need to interpret in order to know what you're looking at. And I'm not saying you can't do it. You can use theory, but there exists no time-dependent multiplet theory that I'm aware of. Or you have to be worried about this in order to make a clear connection, because you measure photons, but you want to know about electrons. You want to know what's happening inside the material. Then there are challenges for theory, as I just said, especially if you use X-ray absorption spectroscopy. There are correlations. You're dealing with core holes. Some buzzwords are Bethe-Salpeter equation, four-particle Green's function. So there's a lot to do also for theory, because these sources are not now only available in the attosecond field in high harmonics, but also in the FELs and the XFELs. You're going to use these techniques, if not using it already. And I think it's an exciting development, but we need also theory for some of these interpretations. So there is an exciting development possible in this whole area. So let me tell you, after providing some of the basic setting maybe for that, about some of the attosecond sources. So as I said probably 5 times already, that the short attosecond pulse provides a broad bandwidth, and I'll show you in a few slides. And I guess in synchrotrons, you would have called this dispersive EXAFs, that you use a broad spectrum and that you cover all the interesting edges at the same time. The problem was with attosecond technology that this was developed based on high sapphire lasers, because they could be handled and we could control them very well. And so you ended up with photon energies at 20, 40, 100 eV. If you now look, I don't expect you to read all these little numbers here. It's just part of a periodic system, but you see I colored a few of them. So for example, carbon is here. The carbon edge is at 284 eV. So already not reachable with some of these traditional high harmonic generation sources. Oxygen 543. If you want to go to more heavy ones, titanium, the K-shell edge is close to 5 keV, right? So this is certainly something that is out of the range of high harmonics, I would say, for quite some time, if not in general. But we could reach, for example, the L edges at 560 or at 460 V. And we have tried to do this very on. I just give you for reference a few papers. So we started already doing this in 2014. Then people looked also at the L edges, also we, and some people have also used M edges because of not being able to go to these high photon energies. But I would say we focused for the reasons that I tried to explain in the couple slides before at K and L edges only. Very briefly, I don't want to bore you on giving the 50th talk to explain high harmonic generation, but maybe just my perspective on it. How it works is that imagine you have some atomic species, some gas, for example, neon. What I show you here is the P state of that, the wave function. If I now apply a strong electric field, this is the field-free case on the left. If I show you here different snapshots in time during a laser pulse. And what you can have is, of course, field ionization, which means you kick out the electronic density, in this case to the top. And since the field can actually change its polarity, it can also pull part of this density back. It generates interference patterns. It's a bit like a mini accelerator, if you will. It takes this electron back and it can either smash it back into the core, where it emits the energy that it has gained from the laser field as light, or it can simply rescatter. And actually, most of the time it rescatters. And this you have probably seen, this 3-step model shown with Coulomb potentials. The whole physics essentially scales. This is the ponderomotive energy, scales with the intensity of the laser field or the electric field and the wavelength squared. And as you will see, especially my group has been focusing over the last 15 or 17 years on turning this wavelength knob. And you can use this as a source of photons. It's not a tremendously efficient source, right? Efficiencies are maybe 10 to -8 or 9. However, you might have 10 to the 15 to 17 photons in one laser pulse. So it tells you that you can still get significant flux out of this. So you can use it as a source of photons with a certain energy. 3.2 UP is a number of what you can get. And you can have backscattered electrons that actually you can accelerate even higher. And my group will using both of these possibilities. Just in a nutshell, why is this challenging? Well, because this whole process is determined by the electric field of the laser pulse. And if you don't have a stable laser field, this is not reproducible and you have low cross sections. So at 800 nanometers, again, I show you the picture. I give you some numbers of the de Broglie wavelengths, of the spatial extent, and of the kinetic energies or currents you can get. And if you scale this with wavelengths, you see that you have a tremendous knob on this and handle. And that's exactly what we were focusing on. The source is nice because you can make short pulses, you can actually play games with the polarization, and it's fully synchronized with a pump field, which is a tremendous advantage. If you do it at 800, you get these individual harmonics. This is just a spectrum showing individual peaks at different photon energies. And if you do this with a short pulse, you see this is a typical spectrum we get. So it's a tremendously broad photon spectrum that we then can really use for these experiments. Okay, I'll just skip that briefly. So in order to do that, we had to develop a lot of laser sources. Nowadays, this is more readily available. But essentially, one of the challenges in developing these laser sources is that materials get damaged when you push high intensity and high average power. And what I show you here is pulse energy versus repetition rate. Average power are these diagonal lines. And just for illustration purposes, you see even the first petawatt laser system in Berkeley was around, let's say, a few 10 watts, 30 watts average power. However, when you look, this is where materials get damaged. And even if you have big systems and big crystals, you can, of course, trade this for repetition rate on the expense of lower pulse energy and at different wavelengths. And so over the years, we have developed a lot of different sources. You see at 2 micron, 3 micron, 7, and currently we even have sources that cover in one spectrum 300 nanometers to 40 microns. And so one part of my group, as Britta has already said nicely, is a lot of laser development, but simply because of these opportunities that we have in X-ray science and using it for electron diffraction. So the lasers are actually just built because of the need of these kind of applications. So I show you a little picture of our setup. We have changed this now a little bit. We have to take a new one, but essentially the laser is in this laser hutch in this black box back there. This is still Ti-Sapphire based with OPA. It generates about 2 micron wavelengths, half a millijoule of energy, and it's nicely carrier envelope phase stable. This just means that the electric field under the laser pulse is the same from shot to shot. And we take very great care to do that. Then you see this kind of square coffin type of chamber, which is where we generate the harmonics. You see a big pump that pumps away the residual gas. And then we have a synchrotron ellipsoid, an X-ray ellipsoid that focuses it into the experimental chamber. Conceptually, it looks very simple. We focus our beam into a small tube. Imagine that's a 2 millimeter tube that we close on top. And the laser drills some holes through it, about 200 microns. And we focus our 2 micron laser pulse into this medium that we fill with helium at different pressures. I show you here a scan of photon energy we measure as function of pressure. And you see if we have pressures as high as 10, 12 bar, then we efficiently generate radiation, basically a supercontinuum over a tremendous spectral range. Now the challenge was, and it took us about 2 years, how to mitigate the flux of gas, right? Because you want high pressures, but it's a bit crazy to put 12 bars of pressure into a vacuum chamber and then want to keep very good vacuum. And it's not static, it's dynamic. And you want to confine it over just about 2 millimeters here, right? You also, even if it's helium, you want to prevent reabsorption. Nevertheless, if you implement something like this, you can have a nice source of X-rays or soft X-rays. And I show you here the spectra you can get and the spectral extent. And yes, you can even go to 600 eV, nice above the oxygen edge, but not with a lot of counts. So we have typically confined ourselves to 1.8 micron because we want to do time-resolved experiments, right? yes, you can integrate an hour on your spectrum and show you have the oxygen edge, but it's relatively pointless if you don't use the source for pump-probe experiments. Recently, we have upgraded our systems, and I think we're ready to start experiments at the oxygen edge, but what I show you has been up to, let's say, 500 eV or so. Another thing we were concerned about is characterization of our source, because we typically speak different languages. In the harmonic community, you talk about maybe some pulse energy. Typically, you talk about brilliance and brightness. So we tried to take great care to get some numbers that are comparable. We also, so we get around 10 to the 7 photons per second in 1% bandwidth at the carbon edge. This is comparable to BESI2 slicing source, which is one of the brightest synchrotrons. However, we have this in 160, let's say sub 200 attosecond pulse duration, which is good news. Spectral stability is excellent. You see up there a measurement. There is a little bit of drift, but within 1% over 16 hours. So that means you can use that as a source to do real measurements. And if you stick in different materials, I show you here titanium disulfide. I also show you a measurement of boron nitride. So these are actually measurements we have done in our beamline. You can nicely identify with good signal to noise the different states, the 3D states, the crystal field split states up here, or the ones in boron and in nitrogen. So this works. So let me now talk a little bit about recent breakthroughs, and I'll give you one example, maybe the unpublished one first, which I'm quite excited about. It's very recent. So we have looked essentially at solids and at molecular systems. And here is one example, an aromatic ring, furan. So the red atom is basically, so it's substituted, one carbon is substituted for an oxygen. And it's a prototype for many things. And many people are, of course, interested in such systems because they have complicated correlated electronic nuclear dynamics, some couplings, basically conical intersection, non-adiabatic transfer through this conical intersection, and on basically all kinds of different timescales. So this is being looked at by many people with different methods. I just show you here the relevant potential energy surfaces, which is, so you go from the Frank Condon region, you excite this ideally with one photon or with several photons, if you will, to this pi star state up there. And then essentially the system can evolve, sometimes people say via one conical intersection, let's say to the left here. Right, then there's another conical intersection, and that leads to ring puckering. This is basically the molecule wobbles around, but the ring is not broken. Or you can go via two conical intersection, this other route down the pi sigma star potential energy surface, and then to a ring opening scenario. And more likely is probably that you have quantum paths with maybe not exactly similar, but not totally dissimilar likelihood, so that probably both kind of pathways are possible. And you want to see, can you follow them? Can you disentangle them? And can you even say something about the branching ratios here? And some of the challenges, especially on this system, is that multiple of these transition states are dark. So if you just use typical spectroscopy, you won't see them. So you have to use theory and speculate on this. However, if you remember, I said that absorption spectroscopy actually measures missing electrons, so to speak, so non-fully occupied electronic states, so it can see dark states. So it's actually a nice method to look at these kind of things. Again, as you already see with these different conical intersections, there are many of them, many couplings, so that's maybe not the simplest system to look at. And the dynamics is too fast to resolve and to energetically identify with many methods. So the idea is that we probe this with from the carbon edge, we take an 1s electron and we see where we can place it. And we excited this with 0.7 eV photons, 17 femtoseconds, so relatively short, but phase stable pulse. and we probe it with this tremendously broad soft X-ray spectrum and our short pulse. And this is a spectrum. I don't really have, I mean, this would be a talk by itself, 45 minutes. So I just want to show you here the differential absorption spectrum. So you see photon energy around the carbon edge, you see pump probe delay, and you see also some Fourier spectrum of it, just to analyze if there are some oscillations, if there is some coherence in the system. Never mind, a lot of red and blue colors are here. You see a lot of different features. I just want to highlight here that we can identify some clear frequency contributions, which you can then, or we can identify from quantum beats between these two different pathways that we see. And then you see actually a very nice transition to one of the main pathways, which is this ring opening pathway. And we can also identify this, in fact, directly and get out the vibrational frequencies that this molecule then has when you have ring puckering or even when you have ring opening. So what I tried to show you here, that this X-ray spectroscopy method can follow this whole dynamics. And even though it's very complicated and intermingle, because you have an energy time spectrum, you can essentially identify the different features because you have 2D information, right? It's not just that you integrate in time or you integrate in energy, and that allows you to disentangle these different contributions. So we can see in this case that yes, we do have these quantum beats. We can put some number on there. They're ultra fast. We see when at one time the population crosses via which conical intersection, and we can say yes, it goes mainly towards the ring opening. And again, we see the vibronic beating at 28 femtoseconds, which also corresponds to this. So we have actually several different observable that confirm each other, and you don't need a lot of theory, in fact, to extract this information, which is nice about it. I'll switch now to some examples on solids. This is actually what we had done rather in the last 2 years or 3 years or so. And I show you one of our first measurements we have done to just see whether this concept really works, which is looking at polyimide or kapton. And you see it has a lot of carbon atoms. You see all these rings, you see oxygens, you see nitrogen atoms and so on. And of course, they have different bindings. Some are double bonds, single bonds, you have different neighbors, and they all can be identified through these different Vogt profiles, or let's say transitions that you can measure. And if you add them all up, so these are the different possible transitions that we should be seeing, they essentially get the black line, and what we measure with our method is the red circles. So this is as good as it gets, and that's how you actually measure such a material, and it allows you then in the reverse process through this multiple peak fitting, which is really established in X-ray spectroscopy, to extract the different contributions, the different transitions and their strengths. So we're quite pleased to see this because we can do this in about 10 seconds, right? So that means if you can do that in 10 seconds, you can start thinking about time resolved measurements, right? If you integrate an hour per time delay, it's a hero experiment. So here you can really try to do that. Okay, so we try to look at something supposedly simple, which is graphite. We have also looked at titanium disulfide. We're looking at HBN and some other materials. I'll tell you in 2 slides why graphite is maybe not as simple. Anyways, graphite is essentially 2 layers of graphene that are van der Waals bonded. So you have these covalent bonding in the plane, van der Waals bonding between the planes. And again, as what I showed you with this little textbook example in benzene, I show you here different binding orbitals. So these are Wannier orbitals. They're called like this in solid state physics, never mind. You have these orbitals in plane, and I just show you one. And I show you an orbital that sticks out between the plane or along the basal plane. And now the idea is, of course, if I want to know what's happening at this material, I should be sensitive to these orbitals. If I measure the spectrum, the absorption spectrum with our source. I show this to you up here. I can interpret this in the different regions. By the way, this is not noise. This is the variance of the measurement that I show you here. These lines that get thicker. And if I analyze this near edge, I can even fit this very nicely with a full DFT code. I even can put in some temperature effects, the Debye-Waller factor. This is actually a collaboration with Yves Joly from Grenoble with his code, which is, I would say, excellent for this. I'm very happy to collaborate with him. And you see it captures really the major features of this measurement very nicely. So black dots are the measurement and red is the simulation. If we analyze the extended spectrum, we can actually get the apparent distances, apparent because it's amplitude and phase. I just show you here the amplitude. And from that, you can pull out the nearest neighbor distances. And this corresponds very well with previous measurements. So again, I check that this works and we can get this information now out simultaneously. We don't need to scan here. So now let's take this whole machinery and do the full time resolved measurement and see if we can really look at what's happening inside the material. Now again, graphite. I thought first graphite, okay, everything's known about it. It's nice. It's a prototype for many things. For example, it's in your lithium ion batteries, and intercalation into the electrodes is one of the reasons why actually the efficiency of the battery drops. It's used in electronics. It's used for future batteries. It's used a lot. Lots of papers are published on it. However, there are still some open questions that are sometimes hotly debated. And one of them is about the carrier scattering dynamics. And the other one is, where do you lose the energy to the lattice, into heat essentially. So the phonon de-excitation pathways. So the problem with this material is, why it's challenging, is that it experiences actually dynamics at essentially all time scales, from the ultra-fast time scale, few femtoseconds, down to hundreds of picoseconds. So it's not so easy to just disentangle essentially electronic dynamics from the nuclear one. So I show you here a band structure. It's state resolved. So the different colors give you the different orbital momentum character. Red is S state, S-like states, and the dark ones are essentially P-like states, PZ and PXY. Also shown down here is the one S state, so this flat dispersionless band that I was telling you about before. Now, the density of states is basically just the integration along the inverse space, and you get this here shown as a red line, and we also multiplied it with temperature, because this was done at room temperature, these experiments. Now, we can interpret these different areas as pi states. So down here, basically these pi states, this is the valence band, if you will. And well, not if you will, it's the valence band. And the pi star is the conduction band. And you have these higher lying states. And they register as these two not so well-defined peaks, I would say, in the density of states. We can directly relate them. They originate from these kind of orbitals, these Wannier orbitals. This is why I showed them to you, right? If you look, pi star has just PZ character. So this is exactly the orbital that sticks out between the two planes. That means if I now can measure the absorption spectrum and I can look at this peak and I see if anything changes on that peak, it gives me direct information about what's happening due to this orbital or due to density changing around this direction, which is represented by this wave function. And likewise for the sigma star, it gives me information maybe about lattice vibration. If the nuclear distance changes in the lattice plane, I should see this as a change on the sigma star. Okay, so we take our soft X-ray source and we just look at the material. We don't pump it at all. And you see, we get perfect match with what we expect. Why is this? Because we actually fulfill what X-ray people know for a very long time, which is what I was ranting on at the very beginning, which is to say you should use well-defined core states like 1s, 2s, 2p. So this gives confidence to interpret then the dynamics that we will see. And then the next step is, of course, that we distort the system, we pump, we move, we shuffle charge from the pi to the pi star state. Okay, that's what happens. Just a few numbers. We use 0.7 eV, 1.8 cycle pulses, high fluence. This is tremendously high fluence. This is fluence that is being used, for example, if you do Raman spectroscopy on the lattice. But we also use 2 orders of magnitude less fluence, and I show you something later, which is comparable to ALPS measurements, in fact. So it's not that you have to pump that high. And you see a differential absorption spectrum, which means pumped minus unpumped. And you see changes also in red and blue, which means positive and negative, actually 10–15%. And we can clearly identify different dynamics. You see here the time scale. It's not totally linear. We show you here up to a picosecond. And we see here the different states in blue and red. You can fit different rise and decay times to it. And already what's apparent is, so you see electrons and holes, right, in these two. However, there is dynamics up here at the sigma star that starts slower, right, maybe a bit later. And you see oscillations on top of it. So we ignore the coherent contribution here. We just use the incoherent background and fit for the moment here. So you can pull out these numbers. And we find out from them that indeed the laser light, I show you here also spectrum and the temporal duration just for illustration purposes, indeed shuffles charges between between valence and conduction band. That was the point. So pi star pumping, okay. However, we see this big change up here also due to some large dipole matrix element, and without going into too many details, because when you actually excite the system, because of the Coulomb interaction and the strong coupling in this material, you change the nuclear position, or the other way around, if you change nuclear position in the lattice, you change the electronic structure. And if you take a differential spectrum, that shows up as a signal. Right? Even if you don't necessarily put charges up to the sigma star state, simply because whatever shifts in electronic states, you will see as a signal here. And we can indeed see that this sigma star is due to nuclear motion. We can also simulate this. We can pull out from the separation of these different curves the chemical potential. We know the material is n-doped. And we see not only electrons, we see electron and hole dynamics in real time here. Right? So we see both carrier types. Okay, let's analyze this. One of the big questions here was electron scattering or carrier scattering. And without digressing too much, the two main processes that you always hear about are impact excitation, which means that at the end of the day, you had one carrier at a certain energy. Afterwards, you have two carriers, so you added a carrier, but you lowered a bit the mean energy. And Auger heating is just the opposite. So if you want to build a solar cell, you want impact excitation. You want more carriers at the end. Auger heating is your enemy in that case, right? So if we now look at two data sets, right, you see electrons and holes here in blue and in orange for basically so 800 nanometers or for 2 micron, you see different cycle period. The circles is the data. So we actually see how the polarization of the material, the distortion of the electron cloud, if you will, builds up and oscillates with the laser field itself. And we see how the incoherent background builds, which is essentially excitation of the system. So electron and holes. And if you analyze this as function of energy, you can pull out, I know this is a busy graph, but I just want to show you here, for example, the number of carriers, the empty blue circles. You see that essentially this goes up, whereas the kinetic energy, which is the turquoise filled holes, just goes down. And it's the same for holes. So in this case, you can say, okay, it's impact ionization that dominates for 800 nanometers, and the timescales are more or less similar. If you now look at this mess down here, you will see that essentially there is a turnover for holes. So there is a competition between the two mechanisms at earliest times, whereas for electrons, again, it's impact excitation. And I don't want to go too much into it. Ask me later if you want. This can be explained as due to a limiting scattering phase space for the electrons here versus the holes. And that's of course interesting, because if you build a device, you need holes and electrons to recombine depending on what you want to do. And so you need to make sure that the timescales for the different dynamics match, or that the processes can occur as you want them to occur. So we could identify this mechanism for the first time, and therefore address this open question on the scattering mechanisms here. So next question was carrier-phonon dispersion, right? So you have, where do you lose the energy from the carriers into heat, essentially? And you have two mechanisms. One is, so you have two strongly coupled optical phonons. One is displacive and one is Raman active. That means if you use current techniques, Raman spectroscopy, you see only one of them, not the other. And so there's a lot of debate. I want to just skip over this one and get to the, just go to this one. It's nicer, sorry. So you see on the top left, basically this shows the different Dirac cones, or the different part of the Brillouin zone. And one is again this displacive phonon, where you have a change in momentum. The other one is this Raman active. And these are the frequencies. If we now analyze the sigma star signal, where we don't really excite, where I said, okay, the signal is there, even though we don't put carriers into that state. This is my clock, which tells me I should be finishing soon. Then, in fact, it is just the basically the decay curve with its oscillations. If we do a Fourier analysis of it, a Gabor analysis, a windowed Fourier transform, there's really no magic where this curve here appears from. You get this time frequency plot directly. So this is directly from the data. There's no theory going into this. And you can then, if you integrate this, for example, here to the left, you see the frequency spectrum, and you can identify all the different phonon modes that you have in that system. And you can calculate the phonon dispersion, the phonon spectrum here, the phonon band structure. And you see different colors here for different electron temperatures. So you can calculate this, and you can identify then, this is the vertical scale is the same as here on the left. You can identify directly these two strongly coupled optical phonons that I've labeled up here as displacive and Raman active. So the Raman active one is the E2G, and this displacive is the A1 prime. Never mind the numbers and the notation and so on. My point is that there is a debate whether both are present, one is stronger, which one takes the energy away. And we can directly see the evolution as function of time. And we see both are present, both are essentially at the same time present, and both are extremely strong. And from analyzing the data, we see that they appear extremely strong. So this is one of these examples where you clearly cannot say, I probe the electrons with my femtosecond laser or my FEL or my XFEL pulse, and the lattice responds much, much slower. No, this is not true. You see here already when the pump pulse, when you disturb the system and the system starts changing, already the lattice reacts. You might not have a full oscillation immediately at the beginning, but already the lattice reacts and it shifts the energetic, the electronic states. And we see both maximize very early, already around 70 femtoseconds also, which is very surprising. And again, the X-ray method, a selling point here is we see all the phonons. We see also the acoustic phonons and the whole dispersion landscape shown in this pretty picture, despite the A1 prime not being Raman active. So there's again a sales point for what you're doing also, and that we can have nice opportunities using these techniques. And we find, in fact, contrary to previous belief, that 90% of the energy is funneled away exactly by this non-Raman active phonon because of the strong electron phonon coupling in this kind of material. So a summary on this, I still have a few slides, Britta, so, but don't worry, not too many. So I hope I could show you a little bit, maybe some things to be careful about, some things that I think are nice opportunities that from my side come out of this Attosecond community, but I think they're equally applicable to your community. And I think there are many connection points on, for example, the X-ray spectroscopy. Notice the line here. The people are looking for the line in the wrong direction. Anyways, it's trying to just emphasize that it gives, I think, a nice, new, powerful tool. It doesn't render the established techniques useless, not at all. I think you need them, but it gives a new perspective that is needed to address some problems. I gave you some examples on the Attosecond soft X-rays as a fully coherent tabletop source. And you can look at some of the publications there on some of the techniques, or contact me if you're interested. I gave you some examples on actual molecules, on solids. I'm very excited about the opportunity that we can follow really the flow of excitation in a complex, relatively complex material, because of the time scales involved in real time and over the whole time range without missing something. I want to talk maybe just 2 slides or so, 3 slides briefly about the opportunities here. For me, this opens a new window into material systems and their functionality to honestly really try to address what I showed to you at the very beginning at this motivation slide with these 4 examples. And I think we have a great opportunity to address these different topics that I just put up here without going into too many examples. It needs some developments. Techniques, we're developing them, right? FELs are dealing with some of the problems and opportunities, or FELs that you're having. We're dealing with the ones in harmonics. I think where we have a lot to gain ground is on detectors. And I think communities like yours is ahead on this. And I think if we can draw from each other on, for example, X-ray detector development, techniques, advanced simulations, especially data reduction techniques also, on how to treat that information, how to beat signal to noise. There is a lot to be gained in this whole area. I don't know if you wanted this, but I tried to put a few things up here on the FELs. I hope I don't insult anybody by being not totally up to date on some of the numbers. I tried to look at the photon energy range and the repetition rates also of, for example, flash or FEL sources. And if I compare and if I think what I would do, and if I take my experience in the harmonic sources, I think RIX is a fantastic technique, which we cannot, I would say, easily implement because we are photon starved. I mean, we have enough photons to do this experiments that I showed you. I think it will be more than enough for any X-ray absorption spectroscopy. But if you want to apply a technique like RIX, which doesn't suffer this core hole problem, I think this is perfectly suited for sources like yours, where you have a huge photon flux. You can apply it to anything gas, liquid, and solid state phase with the issues of damage or excitation limitations. There are many opportunities for the nonlinear variants, for example, even simple things like X-ray nonlinear responses to probe lattice dynamics or things like that. If I look at even higher photon energies, I think it's very exciting because I doubt that harmonics will go much beyond maybe kV, few kV. There's a lot to do, but there are many materials that go beyond that. The high rep rate might be challenging, especially for solids, because of cumulative effects. If you look, for example, at correlated materials, for example, VO2, typically it's an issue to go to rep rates higher than 20 Hertz, right? So 27 kilohertz is certainly too much, or even the kilohertz we are using. Nevertheless, I want to finish here by saying that I really truly believe that harmonics, and not only FELs, not just in X-rays, also in infrared or synchrotron sources, are really complementary and needed in a complementary way. I highlighted the obvious advantages and disadvantages. Harmonics, the stability, the synchronizability is a huge plus. I've shown that we could develop this into a soft X-ray source, a tabletop source. We can do this real spectroscopy with it. This is not the end of it. There are many opportunities, but we have to deal with the low pulse energy, so the photon number per shot. The FELs, at least until now, you're fighting against varying spectra and durations, maybe some temporal jitter, but I'm sure there are many opportunities how to get around this, or to even take it as your advantage, maybe at high rep rates. You know, you can do simultaneous referencing techniques, you can do some single shot detection that we cannot do at the present time, you can use the photon statistics, or you can simply look at a lot of interesting gas phase species to start with. So I think there are many opportunities, and it would even make sense to do cooperative experiments on some of these systems. So I've talked enough. I want to close, but I want to put up my group mentioned up there in black, some people that have just left or finished during the last 2 years that were instrumental to get some of these things going. Especially in the solids, and in blue, a lot of collaborators that I'm quite grateful to collaborating and basically funding. So thank you very much.